Alright, so welcome back to particle physics and the standard model. This is lecture 2 and last time we saw what is a particle, what is particle physics, why particle physics, and we saw that particle physics is about finding newer and newer underlying principles of physics, and that one of the most important principles that we have been using in the last 120 years is symmetries, and we got a little glimpse of how we use these symmetries in the form of Noether's theorem, right. Now we are going to delve some more into this concept of symmetries and how it manifests itself in our world, alright. So to do that, I am going to introduce you to how the world looks at 3 different distance scales or equivalently energy scales, okay. Again we are going to see things that are not completely transparent, but believe me we are going to deal with all of this in very good detail in the class, but it is good to know what are the ingredients of the universe, okay, how to build a universe, what's going on, what are the underlying symmetries, okay. Alright, without further ado, the world at 3 scales, right. First, the world below 10 power minus 18 meters. What do I mean by that? This is how the world would look like if you were to, like Ant-Man, if you shrunk yourself to sizes smaller than 10 power minus 18 meters, right, nano, right, and you looked around, these are the constituents of the world that you would see, okay. Equivalently, because in quantum mechanics, because of Heisenberg's uncertainty principle, energy and distance scales are inversely proportional to each other, right. So, the equivalent is that if you were to go to the very early moments of the universe, okay, to energies higher than about 100 giga electron volt, which is the usual units that we use in particle physics, when the temperature was that high, these are the ingredients, these are the fields and particles that you would see around you, okay. So, what is this scale? Why 10 power minus 18 meters? Does anybody know what this scale is called? This distance scale, also I am sorry, corresponding to 100 GeV in energy. This is the Fermi scale or the electroweak scale, okay. So, what is going on at this scale? There are 5 ingredients, okay. There are 5 kinds of matter fields, okay. So, what do I mean by that? Let me just write it down, okay. I have these, can anybody name these? What are the first 3 called? They are the quarks, okay, but not quite, okay. The word quarks is applied to a few different objects in field theory. Here people just generally call them quarks, okay, but I would just call them QL, UR and DR, okay. That is probably the most precise way to just call them. Why? We will see. And the last 2 are generically called leptons, but again these are not quite the leptons, okay. I would just call them the LL and ER fields, okay. Now these 3 participate in the strong force, okay, the strong fundamental force, sometimes called the strong nuclear force, although it does not have to do with nuclear all the time, okay. And we will see in the course of this course that what we mean by strong is that these fields are invariant under transformations of a particular symmetry group called the SU3 group. The C stands, the C subscript stands for color, okay. And these two objects, they transform, these two objects are basically leptons. So, I will just call them by their colloquial name leptons, but more importantly they all transform under yet another symmetry group in some way or the other, and that group is an SU2. Again we will see what this means. The W stands for weak, and a U1 group, an abelian group, the Y stands for hypercharge, okay. Further, not all of these are actually, not all of these are actually charged under that SU2, okay. Only the ones that I wrote in capital letters, right. So, only the QL, which can be further written down as a doublet, right, and the LL field, which also can be written down as a doublet, okay. So, only these are actually charged under the weak SU2, okay. So, it is this interplay of all these symmetries and what fields transform under what that ultimately makes up the Standard Model at a scale that is below 10 power minus 18 meters or at energy scales higher than 100 GeV, okay. So, I should probably write at higher than 100 GeV, okay. Now, that is not all, because what I have written down here, these are just the matter fields. Why matter? Because these are the fermions of the theory. These are the fermions making up the Standard Model, okay. So, is it obvious why fermions have to make up matter? What if the pen was made of bosons instead?
Occupied the single space.
Yeah, and then the pen would just collapse basically, right. So, you want fermions because they do not occupy the same quantum state. That is how you can actually put them together into a composite object separated in with the ingredients separated in space. Okay, good. So, that is the fermions. What about the bosons? Do you guys know any bosons?
Photon.
The photon, good, okay. The photon is a boson. Higgs boson, okay, very good,
W and Z.
good, okay. So, we kind of got ahead of ourselves here, okay. These are not what you would see in the scale that we are describing, okay. So, I am going to put an X here, alright. So, at this scale below 10 power minus 18 meters, what we are going to see is something called the B boson, okay, and there is only one of them, and then we will see W bosons, but there will be 3 of them. It is not the W bosons that we usually see. Okay, these are also called the W bosons because they are denoted by W, but this is not the W plus and W minus that we usually see. Okay, there is no Z boson. Okay, there is a Higgs boson. It is a Higgs doublet, so it's charged under SU2. What other bosons do we have? Let's go back here. So we've accounted for some of these, right? So the gauge, there's a boson, there's a gauge boson associated with U, that's the B. There's a gauge boson associated with the SU2, and that's the W. So you have 3 of those. What group are we missing here?
SU3.
The SU3, exactly. So what is the gauge bosons associated with the SU3? They are the gluons, right? Commonly denoted as G. And how many of them are there? Does anyone know?
8.
Yeah, there are 8 gluons, exactly. Okay, very good. Okay, so this is how the world would look like. These are the ingredients basically. This is all the matter fields, all the matter particles if you will, and all the bosonic particles that you would see if you were to become Ant-Man and go to distance scales smaller than 10 power minus 18 meters and look down at you. Okay, are we missing something here? Is there some particle that we are missing here in building a universe?
Antiparticles.
Very good. That's a very good point. Antiparticles, very good point. However, in the setup that we've just written down, right, antiparticles are already present. Okay, we will see that when we write down a field, there is no way we cannot write down its, the antiparticle field. So antiparticles are always coming along for a ride. Okay. And then it's also not very clear which one you should call a particle and antiparticle, right? So it's a convention basically. Okay, so what are we missing? Are we missing a force here?
Gravity.
Good, gravity. Very good. We didn't write down gravity here, right? Gravity is present at all scales, right? Or up to the Planck scale at least. So the graviton. Okay, now in this course we will not deal with the graviton. All right, gravity is very difficult to understand at a quantum level. There are lots of there are self-consistency problems. The field theory is very difficult, and it's probably a string theory, probably not. There are dualities through which we understand and so on, and for that you need to take courses on string theory and ADS-CFT, etc., black holes and so on, right? So we are not going to deal with gravity in this course, okay, unless absolutely necessary, but definitely not at the quantum level. We are not going to talk about gravitons in this course. Okay, good. So much for the world at the smallest scales that we know of. Now let's see how the world looks. So how did I write it last time? Yeah, good, okay. So now the world above 10 power minus 18 meters, at least up to 10 power minus 15 meters. Okay. So this is post electroweak symmetry breaking. All right. Basically, at this point the symmetry of SU2 cross U1 that we saw in the previous page, right. So, this symmetry basically gets broken down in a certain sense. Actually what is going on is that this symmetry is hidden in a very subtle way, and we do not really see that symmetry. Okay. So, what would happen is that this symmetry would show itself as a whole other symmetry that we call electromagnetism. Okay. These symmetries combine to form the symmetry underlying electromagnetism. Alright. So, this territory we are more familiar with. Okay. So, now we no longer have the capital Q U, we no longer have QUDL, QUDLE. We have other objects that we are more familiar with, right. So, now we have the electron and positron, we have the quarks, sorry, this is not how you write it, the quarks and antiquarks, right. Basically all charged fermions, or rather electromagnetic charged, right, fermions and antifermions obtained from combinations of or basically obtained from the fields that we wrote down last time, right. Are there any electrically neutral fermions at the fundamental level? Neutrinos, good. So, we also from the ingredients that we wrote down last time, we will also have neutrinos and possibly antineutrinos. We will still have the gluons, okay, intact, because the SU3 did not break, right, the color group did not break. And we had the W's and the B, right, 3 W's and B. So, those would now turn into basically a W plus, W minus, a Z boson and the photon. Okay, 4 degrees of freedom up there become the 4 degrees of freedom down here. Okay. And then most crucially, we no longer have the Higgs doublet that we wrote down last time. Instead, we will have a small h. What is this called? This is the Higgs boson. Okay, the capital H is not a Higgs boson. We will see all this. We will learn all this. Okay, this is a lot of fun. It's one of the most beautiful and important things in physics. Okay. So, the Higgs boson we will obtain as a relic of all this symmetry breaking, alright, and at the end of the day what we will be left with is SU3 color and a direct product of an abelian electromagnetism group. Okay. So, that would be this would basically just characterize the world about 10 power minus 18 meters. Okay. Now, finally, the world above 10 power minus 15 meters. This is past the what is known as the QCD transition. What is the QCD transition? This is where all the quarks condense and then confine. It is a very technical and poorly understood term. They confine to give hadrons, baryons, mesons and so on. Okay. So, now the degrees of freedom are hadrons and mesons, collectively called baryons, right. And you have all the usual leptons, the electron, neutrino and so on. And of course, this is left intact, the W plus and minus, the Z boson, the photon, the Higgs boson and so on. Okay. So, this last is obviously the world that we are living in our natural state, right. This intermediate one is the story of the past century, at least the beginning of the story of the past century, where we kind of discovered all these various species of particles, and then finally the triumph was really understanding what was going on at this scale, below 10 power minus 18 meters, thanks in large part to Glashow, Weinberg and Salam, who put together the Standard Model and really the electroweak theory. Okay. And of course, the story of strong interactions, QCD, was a parallel track in all this with lots of wrong turns and lots of surprises as well. But all of this put together basically forms our understanding of the world that we call the Standard Model. Okay. Okay. So, this is just so you get a glimpse of what is going on. Okay. Now, there is one more thing here that is missing. I wrote down all these ingredients, but there is something I deliberately omitted here. There is an aspect of all this that I deliberately omitted. Are there really only, so let us take these ingredients 1, 2, 3, 4, 5. Are there only these 5 matter fields? Is there something that we are missing? Let me put it this way. So, I talked about the electron, right. It has some mass, some 500 MeV of mass, and then it has it has a charge of, it has a unit charge in fact. Is there any other particle like that? The muon, good. Anything more? It is called the tauon. Okay. So that is the part that I deliberately omitted, because it is a fact that they exist, but we have no idea why they should exist. Okay. Let me explicate on that a bit. Okay. So, that is the puzzle here. We basically have 3 near copies of matter, right. So, we have, for as far as quarks are concerned, we have, do you remember the quarks, the names of the quarks? Yeah,
down,
yeah, good,
up, down.
exactly. So, in particular, if I want a charge of 2/3, right, I have the up quark, the charm quark and the top quark, and then for charge of minus 1/3 I have the down quark, the strange quark and the bottom quark, right. And as far as leptons go, charged leptons go, I have the electron, the muon and the tauon. And as far as neutrinos go, there is in flavor eigenstates at least, there is the electron antineutrino, muon antineutrino and tauon antineutrino, right. And they are all, the reason I say near copies is they are all exactly identical except for their mass, right. Only by mass. So, and we have no idea why there have to be 3 near copies, because there is already, so we already have these ingredients, we already have these symmetries and interplays, and there is a manifestation of those that make up the world. But why you know, if you were God, why do you have to make 3 copies and make them nearly identical copies? Okay, that's the puzzle here. There's an even more fundamental puzzle here. You might even ask, why these ingredients? Why Q, U, D, L, E? And why SU3? Why not SU4? Why SU2? Why U1? Because there are so many mathematical groups available. Why these groups are not other groups? That is also a mystery. Okay, we have no idea why nature chose this realization of quantum field theory to build the universe as opposed to something else. Okay, these are things to which we have no good answer. And the flavor problem, this is called the flavor problem, falls under this rubric. Okay, so this particular problem for why there are 3 copies, right? This is something I personally call flavor problem basic, because there is also a flavor problem there's also an advanced version of the flavor problem. The advanced version, which we may see in more detail later, is that the pattern of masses here, right, which we are not going to get into too much right now, but the pattern here is very peculiar. Okay, some of these masses are too heavy, the neutrinos are excruciatingly light compared to the other. Maybe I'll bring a picture maybe next time for the next class to show this, to illustrate this. So there are various hierarchies among the masses and so on, and then when we rotate from flavor to mass eigenstate basis, there are some mass mixings in the problem. Okay, there are some Hamiltonian induced mixings. The mixing patterns also look peculiar. Okay, and there are other things like CP violation, etc., okay, which we will deal with. All of this put together forms an even more advanced puzzle within the larger flavor puzzle. Okay, so this is the world at 3 scales. Let me take 5 or 10 more minutes to wrap up the class. Okay, now so we saw that symmetries manifested themselves in various ways in 3 different scales. Now even at the largest distance scales, symmetry persists in weird ways. Okay, even through flavor, symmetry persists. Okay, even through these 3 flavor combinations of matter. So what do we mean by that? For instance, it was noticed, I'm sure this was noticed first by Gell-Mann, I'm not really sure of the history, but it was noticed that the hadrons that we have, right, in particular, the hadrons. So can you name some hadrons basically? Any hadrons that you know of? Like what does a large hadron collider use? Protons. Good. So that has to be a hadron, right? Good. Okay. So protons and neutrons are hadrons basically, right? Things made up of 3 quarks are hadrons. So he noticed that hadrons made up of various flavor combinations, right? Like the neutron, which is made up of UDD, correct? This we must have learned in high school, right? Good. The proton made up of UUD. He found that you could put other combinations on an octagon. Okay, I mean you can put things on an octagon if you want, but with some special properties, with some very interesting properties. Okay, so let's see how it goes. So then let's take let me just draw the octagon first. 1, 2. Sorry, it's not an octagon. I'm sorry. It's a hexagon actually. It's an octet, but it's a hexagon. Okay. And he populated it with these hadrons, that's UUS, that's DDS, and in the center you have two different kinds of hadrons. Both of them are UDS actually, okay. They only differ by whether they are symmetric or antisymmetric under flavor exchange when you write them as a quantum state, okay. Did I write everything? Yeah. So this is DSS. You can already start seeing a pattern, right, when I put it this way. The pattern is this, the first row contains no strange quark, right. The strange quark content can be called strangeness, obviously, for obvious reasons, right. So the first row contains no strange quark. The second row has a strangeness of -1, okay. So you assign -1 to a strange quark basically, okay, in the old convention. The third row, because they contain two strange quarks, you can assign, the third row basically corresponds to strangeness of -2. But that is not all. If you look in this direction, in the diagonal direction, right, this central diagonal you will notice has charge of an electric charge of 0. These are all neutral, electrically neutral, right. And this one, obviously I put a minus, has a charge of -1, and this row has a charge of +1, right. So they all fit into some nice pattern, and using, just by drawing these diagrams, Gell-Mann was able to predict the masses of new mesons or new hadrons that were not discovered yet, okay. So this is another use of the symmetry principle, a very neat use of the symmetry principle. So this particular one, because it contains 8 baryons, this is called the baryon octet, okay. There are other fancy things that you can draw. Let me draw one of the famous ones. So if these are baryons, what are these that I am writing down? Mesons, yeah, these are just mesons, good. Yeah, and this has a very particular notation, it is a K bar actually, okay, K bar 0. This is the meson octet, and you can assign charges and strangeness in a very similar way, and I encourage you to go and look up the contents of these mesons, okay. So yeah, so that is a pretty neat application of the symmetry principle. There is also the baryon decouplet that I am not going to draw here, but I encourage you to go look up all of this in Griffith's text. Okay, for the first half of the course at least, I will be closely following, at many places I will be following Griffith's, I do not quite remember the name of the book, but it has the word particle in it, his famous particle physics book, okay. Alright, so we will stop here, and in the next class we will see how we can use further symmetry principles to further understand the stability of some particle species around us. Thank you.